Hello, my name is Anthony Vidana. I was an Apollo engineer in Downey working in Building 4, and this video is going to describe a little bit of what happened in Building 4 with simulations. So here it is. The Apollo simulation complex aided manned spaceflight training. Many elements of the orbital flight reenacted in this unique facility. The simulation complex helped familiarize astronauts with in-flight characteristics of the Apollo spacecraft. The computer and supporting elements warehouse in that simulation, both space flight motion with man-in-the-loop and operation of two Apollo major onboard systems, a stabilization and control system, and guidance and navigation system. The facility, which included a full-size Apollo command module mock-up, the engineering tool. The complex was developed as an engineering tool for the design of NASA's Apollo spacecraft command and service modules. It performed all the essential functions of the spacecraft system for the Earth orbital phase of the lunar mission. All elements of the Apollo orbital flight, from the moment the S-4B Saturn V third stage cut off to parachute deployment, can be displayed through instruments readings in the cockpit. Apollo astronauts participated tests simulating such flights. Previous use. The first unmanned Apollo suborbital test flight mission, AS-201, with spacecraft 009, was simulated well in advance of its successful February flight. Apollo Saturn mission fully simulated 18,000 miles mission. The spacecraft guidance and navigation systems. The simulations are carried out with the aid of the world's most accurate, at that time, Earth sphere and a real-time computer and simulation systems, drawn to an accuracy of 1 inch equaling 100 miles, and 6-foot globe including 31 of more than 250 landmarks, used by the astronauts in actual flight. An intricate scanning probe 1 inch from the globe and a closed-circuit television system pictured that is a picture of the Earth and a star field as they actually look to a spacecraft orbiting at 100 miles. An Apollo space table called a dynamic motion simulation sways and pitches like a spacecraft in flight in response to commands of the Apollo test crew or the automatic control system. It rotates, and inertial sensors detecting the motion relay signals to the flight crew instrument panel and control system. Receives advice. Similar to actual flight, the Honeywell-built stabilization and control system receives manual instructions from the crew and electrical advice from the internal sensors and guidance computer to general commands that cause the computer module or flight table to pitch, roll, or yaw. The guidance and navigation system built by MIT provides inertial guidance, altitude, reference, and optical navigation. It works semi-automatically, providing guidance for the stabilization and control system and other major systems in flight. Laboratory proof. In spaceflight, unlike aircraft testing, we can't gradually build up experience by first taxiing around and taking short hops. The first flight is the real deal, so the use of a mission simulation to prove out the spacecraft system in the laboratory, the studies duplicate anticipated spacecraft flight motion performance so accurately that a high level of confidence in the design of the spacecraft systems. Man in the loop system mission evaluations studies required a simulation spacecraft command and module wooden mock-up called an evaluator. It was the equipment needed to provide the flight test crew members with a realistic environment. It is a full-scaled, has up to 3 flight couches and a complete set of controls and displays, most of which are optional. Simulations. A real-time digital computer and 4 consoles of analog computing equipment, approximately 500 amplifiers, provided the real-time simulation computer's capability. The computer has 32,000 word memory with a cycle time of 1.75 microseconds, which means it can perform approximately 600,000 arithmetic computations per second. The scale of the Earth's sphere is 1 to the 7 millionth, 1 inch representing 100 miles. It gives undistorted optical view of the Earth's surface, as close as 0.5 inches, or can be used for the viewing of the entire Earth out to 360 inches, 36,000 miles. The document shown on the screen shows complete detail, and this thing is loaded with calculations how this simulator was operated and the calculations used to produce them. It also has some same photos shown in this presentation. I was really impressed with this particular book, and has for people who want to do more study on this particular simulation system, they should go to this particular manual. It's online and take a look at it. I'm going to switch gears a little bit and describe some more equipment that was in that particular building 4. This building had one of the largest computer complexes west of the Mississippi that had IBM equipment. It was really impressive. It had raised floors and a multitude of equipment in that particular. This shows the raised floors that were there, and a little bit of detail on what a raised floors is. There's a picture of the raised floor as they're putting them in and out, and these things would get loaded with cables. And there's a view there of what the cables looked like. It was like a resonance. Some of the later computers started using water, so we had pipes in there too. So there's a leak detector I put in there that would help detect leaks on the system so it wouldn't crash. And here's the computers that were used there. It was the model 360, 85 IBM 360, and later on, they in the 70s they started using an IBM 370 model 168. So they also had a photography, a lab that took care of some of the pictures for the facility and also for the stuff that was going on in the simulators, and they were made into cards and a lot of different things that they had in there. So there's some of the people looking at some of the photos, and here's the entry room. Goodbye for this. This is the end of this video. Thank you for watching my video, and this is the end. Thank you. Bye now.